Welcome to the American Society of Quality Lean Enterprise Division 2015 webinar series. By listening to our webinar series, you will get the best of the best in the lean industry. Stay tuned to the end of this recording for more details. This month, our speaker is Martin Hinckley. Martin is the founder of Assured Quality and author of Make No Mistake. Now, let's join Martin as he presents what is world-class quality and how can we achieve it?
Thank you, Paul, and I'd like to thank you for the invitation and welcome to all of those who are participating. Today we're going to be talking about what is world-class quality control and how can we achieve it. We all have different ideas of what world-class quality control consists of, but today we're going to be talking about what the world-class standards of that quality control are. So to begin with, the first participant poll is, what is the primary quality control method in your company? Are you using Six Sigma or Lean Six Sigma? Do you use ISO 9000 or some other ISO standard? Is mistake proofing the primary emphasis, or do you have other quality control methods? Take a minute and answer the poll question.
The results are coming in, Martin. We'll close it here in just a second. Looks like the results, Martin, 21% Six Sigma or Lean Six Sigma, 49% ISO or other standard, 9% mistake proofing, Poke-OK, and 21% other.
Excellent, thank you. One of the most important questions that you can ask is, does your quality control pay? In other words, are you saving more than you're investing in your quality control efforts? We're also going to talk about the secrets to mistake-proofing devices and then controlling variation with settings rather than through statistical process control. This study was conducted by the Xerox Corporation in the 1990s. It included companies that were using Six Sigma, as well as companies that were generally focusing on traditional statistical quality control methods. The data here shows that most companies had defect rates in the range of 1,000 to 10,000 parts per million, and that the cost of their quality control effort, which included scrap, rework, repair, warranty, and quality control, was an astounding 6 to 24% of their production budget. This is the view that quality control is expensive. Now, what is interesting is that many companies confuse the tools that they're using with whether or not they're achieving outstanding quality control. The difficulty is, for example, there's one company that I know of near me in the Logan, Utah area that claims to be a Six Sigma company, but their own data on the defects in their records is that 8% of the records have defects in them, have errors in them. Well, an 8% defect rate isn't anywhere near the expectations or standards of Six Sigma in terms of the actual defect rates. So outstanding quality control does not depend upon the tool that you use. It is measured in the results that you achieve. This same study concluded, again this was in the 1990s, the world-class leaders in quality control were consistently maintaining their defect rates below 30 parts per million. And these same companies were spending less than 3% of their production budget on scrap, rework, repair, warranty, and quality control costs. This constitutes the view that quality control is free. In other words, what they invest in the quality control effort is almost paid for by the outcome in the results. So these represent the two dominant views of quality control that existed in the early 1990s, that quality control is either expensive or that it is nearly free. One of the questions that we have, though, is why do most quality control efforts fail in the sense of achieving world-class quality? And the rather remarkable reason for this is that statistical process control can't predict or control defects. Now that sounds like a contradictory statement, given that many organizations heavily focus on statistical quality control methods. But the truth is that, that none of the statistical methods are accurately predicting modern defect rates. The big problem is that most defects are caused by mistakes, and mistakes are rare random events. They don't happen very frequently. Most defects happen because mistakes happen, and mistakes are rare and random events. You can't predict when they're going to happen. You can't predict how severe the outcome will be when they happen. And because of this, statistics are an ineffective tool in dealing with the problem of mistakes. Deming said, "In God we trust, everyone else bring data." Well, here's data that illustrates the problems of mistakes versus the traditional view of variation. This curve at the right is a parabola. It's actually the bell-shaped curve of a normal distribution, but it plots as a parabola when the vertical scale is logarithmic, as shown on the left, which is plotted as a probability distribution function. If this were a task such as drilling holes, the whole distribution diameter could be described as this parabolic curve or a bell-shaped curve of a normal distribution. The lower specification limit and the upper specification limit illustrate control limits on that whole diameter. And as we look at the bottom edge of the curve, we see that very little of the curve falls outside the lower specification or the upper specification limit. Based on statistical methods, we would predict that we would have very few defects. In fact, this curve would give you the 3.4 part per million defect rate that we expect from Six Sigma. The problem is that occasionally a worker may forget to drill a hole if this is being done manually. And the drilling omission is larger in height than we would predict would ever occur from the statistical problem, and the outcome is further from the control limits than we would ever predict would happen based on the statistical standard. More importantly, if we were trying to predict how frequently a mistake such as this would occur, and we were doing sampling and inspection of sampling 1 in 100 parts, just to characterize the frequency of this one mistake, we would have to have 100 million operations to accurately predict the probability of this mistake. Well, therein lies the problem. We never get enough data to understand mistakes correctly. The principles of DMAIC, of measuring, don't work very well in terms of understanding mistakes in the roles in terms of overall quality. Now, there are lots of other mistakes that could occur. You could pick the wrong drill. You could machine a hole partway through instead of going all the way through the part. You could machine the hole in the wrong location. The drill could break. The problem is there are just many, many kinds of problems that occur because of mistakes, and none of them fit in the boundaries of what we would call the distribution of probability, and they're completely unpredictable. Here's examples. We had a product that was out in the field, and every time we had to respond to the problem in the field, in addition to writing a report, we took a picture. It made it very clear that almost every problem that we were dealing with in the field was a mistake. Here's a missing cable clamp. The clamp should have mounted on those 2 threaded holes that are near that tube, and the cable clamp should have held that tube in place. Here's a nut that was dropped in a part and left in a part. And then there was a plastic piece that was put in to keep small parts from falling down into the product as it's being assembled, and they forgot to remove the plastic part. There's washers, thick washer or thin washer. If the washer's too thin, the bolt bottoms out and may not clamp the parts correctly. If the washer's too thick, we may not have enough thread engagement. We see bent pins, and then on the right, the tube should come out straight, and instead it's bent at an angle that's far off of what we would consider a distribution or variation in terms of the tube alignment. When we started collecting data from actual production processes and what people were having problems with in the field, virtually all of the problems tended to be mistakes. So the question is your quality control like traditional statistical quality control view? Is it expensive? Or is it like the traditional mistake-proofing view that quality control is free? Today, we're going to introduce some new ways to think of quality control that shows that it's not just expensive, it's not just free, but that you can achieve outstanding quality control in a way that pays you to do that. So here's our next participant poll. How would you characterize your company's quality control effectiveness? Is it expensive? Do you view it as being free? Does it pay you to do it? The savings are greater than the investment. Or 4, I don't really know where we stand. Please enter your poll response.
The results are coming in. We'll give them just a second here, Martin, and I'll get you the answers. That was a great explanation just a second ago. I'd never seen it explained quite like that. Looks like the
Paul, do the users, participants hear what you're sharing with me on the poll results?
Yes, they do. So the answer to the poll is 33%.
Thank you.
It is expensive. 13%, it is free. Costs are balanced by savings. 22%, it pays. Savings are much greater than greater than the investment, sorry. And 33%, I really don't know where we stand.
Very interesting. And that's one of the challenges. A lot of times we don't really know where we stand. This is one of the most important sets of data on quality control that has ever been produced. We set out to examine what is really linked with the defect rates and what we do that makes a difference. We couldn't find the correlation between statistical process control, process capability, and actual defect rates. This chart shows the complexity and versus complexity, the defects per unit for products produced at Motorola and a disk drive company. This study has been reproduced at Applied Materials and at GE aircraft engines. The correlations for this data are 0.96, the highest correlations we found for any effort to compare quality characteristics. And the trend is also very strong because this is a log-log plot. It shows that as the assembly complexity increases, the defects per unit increase. It also reveals that there are 2 completely different ways to improve quality control. And the first is I can move to the left by making my product simpler and while reducing my defect rates. And you notice that the disk drive company has more defects than Motorola. The second way that I can improve my quality control is I can change my quality control to move from a company like a disk drive company down to the position where Motorola is at. So that tells us there's 2 primary ways for influencing quality control. Well, this data is useful and interesting. It demonstrates that one of the most important things in quality control is the role of complexity in the relationship to both mistakes and variation. As a task becomes more difficult, we increase the mistakes and the variation that are occurring in the process. And so one of our greatest opportunities in terms of quality control is to simplify the products, the processes, the tools, the equipment, and every single thing, the testing, the instructions, every single thing we do in the process. Although that data was interesting, it is not a very broad study in the sense that we weren't able to collect data from a large number of companies. This set of data represents over 600 companies that delivered a product to an OEM manufacturer, and where they assembled a product from all of these different parts. Each dot here represents the average cost of the parts sold to the parent company. And on the left is the average defects per unit of the products that they sold. Now, what is remarkable about this data is, first of all, for a given price, the defect rates from the highest to the lowest are 5 orders of magnitude difference, or the defects at the top of the chart are 100,000 times greater than the defect rates at the bottom edge of the chart. The correlation coefficient here is not very great because of the large differences from company to company in terms of their quality control. But for a broad sample of many companies, from software to very complex electronic devices and complex mechanical devices, this is the highest correlation that we've seen in any kind of data. But the real important statistic is the F statistic says with this data, it is virtually impossible that this is not a correlated set of data, that this is a true and strong cause and effect relationship. The F statistic says that there's less than 1 chance in 10 to the minus 43 that this is not a true cause and effect relationship. The red line represents the least squared fit to the data, and it says that the most important link that we can find in terms of quality control is first simplifying it and then changing the level of our quality control. So if I'm a company represented by the red diamond at the top of the square, I could try to improve the attractiveness of my product by making workers work faster. Well, what's going to happen is the defect rate is going to go up. My price goes down per part, but my defect rates go up. I could try to improve the attractiveness by lowering the cost of my part without changing my production processes. And in that case, my defect rates remain the same, and I actually am less attractive to the parent company relative to other suppliers because my defects are higher for this, even though my costs have gone down. If I want to move in a direction that is going to eliminate the problems that I have and make my product more attractive, I have to make things simpler. That's one of the most important things you can do. And typically, you can make a bigger change by simplifying products, processes, tools, and equipment than you can with Lean. This complements Lean. They work extremely well together, but the process of simplifying everything that you do should be the focus of the ongoing Kaizen as well as the product development design. Now let's talk about the differences in quality control in these companies. In this set of data, it represents over 320,000 defects. There are 10,000 quality action reports. In this 320,000 defects, excessive variation was mentioned 5 times. Every one of the problems described in this report, in the report that covered all of these problems, were missing parts, wrong parts, misrouted, design errors, misread drawings, using the wrong version of the drawings. Virtually every problem of these 320,000 was a mistake, which says that if I want to move downward in this chart to reduce the defects in modern production, one of the most important things that I can do is to get mistakes under control. If you don't do mistake proofing, no matter what else you do, you will never have world-class quality control. There are, however, in this set of data, 800 companies that are not represented. The reason for that is these 800 companies did not have a single defect in the products that they reported. You can't plot 0 defects on a log-log plot. What appears to happen, and one of the most stunning and surprising results, is we saw no data points in the lower right-hand corner. But what appears to happen is companies get better and better and better in controlling their mistakes, and then they fall off the chart. There's no defects in these companies. They get to essentially perfect quality. One company claims they've completed 26 million operations without a single defect. So this data is worth billions of dollars. It shows you, this one company, we demonstrated that with modest changes that they could save $10 billion over a 10-year period on a $5 billion procurement budget for these parts. It shows that there are ways to save huge amounts of money as well as to improve your quality control. On the left is a simple cable clamp. You find these in the electrical panels in your house. They hold the wiring. It has 5 parts and 9 assembly operations. On the left is a modern cable clamp made of plastic. It has 1 part and 2 assembly operations. It has printed on the outside perimeter, this edge goes inside the box. It even shows you how to install it. By simplifying the products and the design, we eliminate hundreds and thousands of types of mistakes that can occur, and we can't overlook the importance of simplifying processes and products to get to outstanding quality. And this is a huge money saver, and typically the cost and complexity and the assembly time can be cut in half. Here's just a few examples of real products. These are products, fairly complex products. This one product is a tapered product. It's made with a scarf joint. The scarf joint isn't vertical, and it doesn't cut straight into the center line of the circle. It's cut at these angles. This set of complex plastics parts, a set we were paying $5,000 a set, and these parts have been made this way for 20 years. Well, by redesigning this into a flexible part, the first part we made, including the cost of the mold, cost us $500. And the part after this first mold was made, the parts cost $20 a piece. The tooling to install the scarf parts cost about $20,000, and the tooling to install the redesigned product cost us $200. It achieved the same quality. The reliability was much higher, and we had fewer defect rates because we had a lot fewer operations. And so it improves reliability, it cuts the costs, we speed up the development, and we have fewer defects, scrap, and rework. Here's an example of complexity that we see in typical processes. We went into one facility, and they have and-on lights, which is based on the Japanese model that rolls up and shows the status of a production line. You notice the controls here, though. There are 7 buttons. There are 3 knobs and 2 key controls. And the problem is you can set the machine wrong. You can not have the key handy when you need to change it. The controls are extremely complex. Here's a better solution. Here's a case where you take the knob in the center and you just turn it to the pointer, and it lights up at the top where you set the pointer. You can look at the pointer and read and interpret what the lights mean. But there's one other problem here. Notice that below this there's a board where the workers bring their tags. If they have a problem, they have to come to this board and switch the light to show what's going on, and then change the tag to show where the problem's at. The difficulty is the workers are leaving their work when they have a problem to come and set the and-on lights. That's not the intention of and-on lights. The and-on lights come from the and-on cord shown here on the right. The idea is if you have a problem, you pull the cord. In the automotive industry, the original implementation, the line would not stop for 60 seconds until after the cord was pulled. There's much simpler solutions. We could have at each workstation a red light to show when I have a quality problem or an assembly problem, a yellow light to indicate that I'm running low on supply of parts, or I can have a green light to reset it, and then the and-on lights at the end roll up the conditions along the line. You see how simple set of lights or an and-on cord are versus the operation of these complex and-on lights on the left. We always are looking for making products, processes, everything we do simpler, easier, less expensive. So here's the next question. Six Sigma problem-solving method, DMAIC, is very effective in mistake proofing and in simplifying products and processes. True or false?
Martin, while everyone's doing that poll, I had one question that came in. How did you get the data that you presented back on it was about slide 17, I think it was the one that had the log regression with all the companies. Where did that data come from?
Okay, I'll answer that when you get the answer to the poll here.
Okay, it looks like 54% true, 46% false.
Six Sigma, the DMAIC method is not very effective in mistake proofing. And the DMAIC method is also not particularly effective in making products and processes simpler. We'll show you a method that will help you address some of those concerns. One of the questions that came in is, where did the data come from those 600 companies? We were doing a study. I was working with the University of Utah, teaching in the business school, and we were working with a major aircraft manufacturer, and they provided the data for an entire year for every single company that provided products to that aircraft manufacturer. So it's a very large set of data. It included every quality problem that they encountered for a whole period of a year. Okay, so 6-step, the SMS mistake proofing method, 6 steps to world-class quality. What do we need to do to get there? Well, the first thing is, like many other steps, we discover and select the problems we're going to work on. We analyze the problem. But the next 2 steps are the things that change from getting good solutions to getting great solutions. The first is that we require that you always generate many solutions. There's always at least 5 ways to solve every problem. You never know if you have a great solution until you've generated 5 and do a comparison and selection. What we do is compare. We blend the best attributes of the concepts that we generate and then select the best solution. We deploy it, and the next step that is a little bit different than DMAIC is that there's an evaluation, and from that evaluation we share that with the intent that others can take advantage of that so that it can be deployed broadly. This simple pattern results in outstanding improvements in products, concepts, mistake proofing methods, and every type of method you have as you approach quality control. I'd like to talk just briefly about devices that control mistakes. Most of the training that approach to mistake proofing is to show a lot of examples. Unfortunately, presenting a bunch of examples has very limited effect in helping people develop mistake proofing solutions. We've seen many cases where we show a bunch of examples and then ask people to create a mistake proofing solution, and they have great difficulty doing that. One of the problems is the examples shown may not be particularly relevant to the problems that you face. The second problem is that each mistake proofing solution tends to be quite unique to the problem that is being solved. And the result of this is novices have a great deal of difficulty generating good mistake proofing solutions. A third kind of problem is that they may not remember the examples that were shown sometime later, or the examples shown may not be the ones that they really needed. Our SMS mistake proofing method is quite unique. It provides a way to find solutions, and it works as well for novices as it does for experts in mistake proofing. So what do we do that's different? Well, the first thing is we classify the problem. There's these 5 major classifications, and then under them some sub-classifications, but we try to identify what was the outcome of the mistake, not the causal factor, because we can't control all the causal factors. What was the outcome? It could be something like an omitted part, or we committed a prohibited action, committed something that we shouldn't do. From that classification, we have developed a set of solution methods. We then review the solution methods that are useful in fixing the problem that we've identified. What this does is it narrows down our search. Instead of having to look through all the possible ways to solve a problem, we have a very finite set, a small set of ways to look through to solve that specific problem. And then we use that to find examples. We find an example of how someone translated this solution method into a real solution. It may not always be in our industry or field, but it gives us an idea of how that method has been translated into a concept. Mistakes have been classified in lots of different ways. They've been classified by behavioral factors, causal factors like fatigue, priority, or interruption, cognitive factors, errors in thought processes, human error probabilities, stress factors, workload, life changes, frustration, environmental factors, noise, lighting, mistake consequences, injury, loss, damage, delay, or corrective action, rework, repair, or scrap. The problem is that classifying these mistakes in these kind of categories doesn't help us in any way to come up with outstanding mistake-proofing solutions. They don't lead us to the skills that we need to come up with mistake-proofing examples. So we classify them by defect types. We don't have time today to go through all of those. We'll show you just a few brief examples. But the key for novices is that the single most important enabler in developing outstanding mistake-proofing solutions is being able to find useful, relevant examples, to find a solution that is like the solution I need to solve my problem. And the most important way and the fastest way we found to do that is to search by type of classifications. So here's 5 basic defect types. I'm going to illustrate one major classification, show you how we break that down into subclassifications. If we can't see 5 ways to fix it, we always try to classify a defect into at least 2 different ways. That gives us different ways to solve the problems. We have 2 substantial resources. One is Make No Mistake. It contains over 200 examples that are sorted by classification, so you can look up examples. We're getting ready to launch a new product that is an online classification tool, and it's available at no cost, where you can look up and find examples. You can search in many different ways. There's 400 examples. It's easy to search and look up. It's very easy to enter and add examples to the database. The total data entry time takes about 15 minutes. In one page, you see what the problem was, when it was solved, where it is located, what team solved the problem, the evaluation. Did it prevent the defects? Was it low cost? Did it improve output? Does it require a lot of upkeep? How the problem was inspected, how it was controlled, and then a before description and after, preferably with the pictures that also will show how you classified it and the solution method used. Now, this database is searchable by keyword, by title, by before and after descriptions, by the results. The total data entry for a problem takes less than 15 minutes. To put this in comparison, I went to one company and they'd prepared a 100-page report on a serious quality problem, and at the end they wrote, "No action taken." For the cost of preparing that 100-page document, they could have implemented 5 or 6 mistake-proofing devices that would have solved the problem that they had and would have also prevented 5 more problems from happening. We need to think about simplifying the documentation and improving the results and putting the focus on action taken. This will also track how fast you get your problem solved, and it will give you reports on your performance. This particular example comes from anesthesiology. It used to be that 1 in 10,000 people died in the operating room because of an anesthesiology error. The equipment was such that if you turned the knob to the right on some equipment, it increased the flow of oxygen, and turning it to the right on other equipment shut off the oxygen. The anesthesiologist would work in different hospitals, and so they would kill patients as they thought that they were turning the oxygen up when they're in fact turning it down. Notice here the bar that protects the knobs from being bumped. Notice the color controls between the flow meters and the gauges, and each gauge has a different neural pattern so that you can tell where your hand is at just by putting your hand on the knob. So here's some classifications with information defects, and some of the ways that we think of classifying information defects is confusing information. You will really be lucky if you can get this person to work for you. Does that mean you really want to hire this person or you don't? Or will you really be lucky if you can get this person to work for you? We couldn't get him to work for us. Or you'll really be lucky if you can get this person if you can employ this person. This is confusing information. Here's another example of confusing information. Incorrect information. Information is provided, but it's incorrect, such as a faulty gauge. Misread, mismeasure, misinterpret. You have the information, but you didn't read it correctly. You have missing information defects. The information isn't provided at all. Or an inadequate warning. A warning is given, but it's not adequate to get the attention of the operator. Here's a burner with a stove with 4 plates and 4 controls. Which control operates which burner? You know, what's interesting is you can train operators, you can tell them, you can mark this. No matter what you do, people are going to turn on the wrong burner. And what's interesting is when we walk in facilities, in every facility we see serious problems with a lot of the controls. Here's an example of one company developed a way that can fix that. The link between the controls and the burners is obvious at a glance without explanation. It also illustrates, however, the importance of thorough mistake proofing. There's one extremely serious problem here. If I lift that pan off the stove, and as I'm lifting it towards me, the bottom of that pan hits one of the control knobs, the boiling water, I can dump that right down the front of me. Now, GE stopped making this stove, and I'm sure it's probably because of that problem. The problem could have been solved by making control buttons that are flush on the surface, and then there wouldn't be any problem at all. But I've seen recently that a manufacturer out of the country is starting to sell this type of stovetop in the United States again. One trip I was on that had burners, and it had a circle around the control and a line over to the device it controlled. A lot of times we can't change the equipment, but simply by changing the marking we make it obvious which control operates which device. Misread, mismeasure, misinterpret. This type of problem is common. The person is executing a step. They're supposed to be drilling a hole. They're on step 16. Work on the equipment, glance over at the instructions, and they read 32 on the diameter, cut the part. Now the part's scrapped. It can't be repaired. To solve this type of problem, the solution is very simple. You should ideally have only one step visible at a time. You may have preceding and subsequent steps in much smaller print on the page, but there should be one large page of the explanation of the step that you're on, so it's not easy to get confused on where you're at. And ideally, this should be vertical so it can be read across the room. A lot of times you have to do the task away from the instructions. Missing information. A person was performing an assembly, and someone came into the room and said, "I'm sorry, we have to, your spouse just went to the hospital. We need to call them, and we need to get them, you need to leave immediately." He was distracted, left. Someone took over the assembly. They missed one step. They failed to connect a connector. This was on a destructive test of a multi-million-dollar article. It was a pull-down test where it slammed into the ground at 200 miles an hour and is completely destroyed, and they didn't get any data out because this one connector wasn't mated. Again, if you have one instruction visible at a time and you can't advance until that instruction is completed, when another worker comes up to that equipment, they know exactly where you are in the process. They don't get confused on where you are or what the next step is. Here's the dipstick selection. What is this dipstick for? Is it for oil or for transmission? If you get them confused, you can put oil, transmission fluid where you can put oil where the transmission goes and ruin the vehicle. Well, here's how one company solved it. They put O for oil and T for transmission. This only has to be explained once, and it's very easy to get this correct. And the dipsticks are made so they're completely non-interchangeable. We use the classification. Once we classify the problem, we use the classification to find alternative solutions for our problem. After selecting a problem, we classify it to develop solutions, 5 solutions if possible, by first reviewing solution methods that have succeeded in solving similar problems. And the methods are grouped by classification in solution sets. And here's 6 ways of more than 50 ways that you can prevent things being put in the wrong orientation. Here's a vessel that needs to be attached. You notice it's got 4 mounting screws. The fittings are the same. It can be put in upside down, and it could be put in with the vent fitting on either end. 4 ways, only one of which correct. Here's the way that this problem was solved. The fittings and mountings on the 2 ends are opposite. Notice the yellow line for the circular connection, the flat on the other end. And then on the bottom, it was designed so that there was a offset pin that went around this conical surface, so the fitting could only go in one place on the bolt pattern. This cut the assembly time from 2 hours to 7 minutes. It eliminated lots of fixtures that were added and removed to prevent parts from being installed incorrectly, and it completely eliminated the problems of getting the parts in the wrong orientation. An alternative solution is to make parts symmetric. We can put a spring groove on both ends so it doesn't matter which way we put it in. Or we can move a rib so it's in the middle rather than non-symmetric. Oftentimes, ribs are just slightly offset, and if they just made them a little different, they could make it symmetric and eliminate the mistakes as well as reduce the cost of making the parts. Instead of having 2 holes where if we put it in upside down, we could have 4 holes. So it's always we always have the right holes, or we could put maybe 1 hole in just the center. So my next question is, Toyota a Six Sigma company? True or false?
Martin,
Toyota is a Six Sigma company.
Martin, that was great, just great stuff. I mean, I just love seeing that. I had questions about, would you consider making the slides available?
Yeah, we can talk about that.
Okay. We'll for everybody listening, I'll figure out a way to make sure that everybody realizes they are available. Before we end this poll, one other question. You talked about that online search system. Is that system up and available now?
Yes. It will be available after the May meeting of ASQ.
Okay. The poll results. The poll results: 24% true, 76% false. Also, before we get any farther, if everyone would enter any questions.
Toyota is not a Six Sigma company.
Excuse me, Martin, if anybody has any questions, please enter them. And this was the last poll question, and we'll answer all the questions at the end. Go ahead, Martin.
Thank you. Toyota is not a Six Sigma company. Since the 1970s and 80s, their goal has been to completely eliminate statistical process control from the factory floor. Shigeo Shingo, when he visited Sanford, was asked what he thought about Six Sigma, and he lifted himself up by his arms to his full height in his chair. He was 90 years old at the time, and he answered with one word, and he said, nonsense. they don't use Six Sigma to control variation. And we're going to talk about how to control variation without statistical quality control methods. And we're going to look at how they control variation by turning adjustments into settings. Now, in the traditional method of making a product, think of this as a tool holder and a tool in a milling machine. We don't see the motor and the head and the equipment. We're going to cut a groove in the part, which is going to slide out of the screen towards you as the tool is turning. We're not going to show the turning, but it's turning as we cut it. We cut the groove, and when we finish cutting it, the tool is not exactly the same as when we started. It's worn a little bit, and I'm going to greatly exaggerate the wear. But when I take it out, it's not in the same starting position. Now, it may be good enough to make 5 or 6 parts, and the tool may not be worn out, but what I do so that I can make good parts and make some more parts without throwing the tool away is I adjust the head, the tool holder, and the tool downward. I make an adjustment. And statistical quality control is all about rationalizing when and how to make adjustments. I look for conditions that are out of control in terms of the X bar or the mean, and that's the circle points outside the control limits, and the range. And whenever I wind up with a point outside of those values or a trend or other kinds of anomalies, then I make a decision about whether I need to make an adjustment. That's the way that traditional statistical quality control methods work. However, the whole problem can be avoided by converting our adjustments to settings. Here's how they do that in terms of the wear of something like a tool like this. We use the same kind of process. We have a milling head tool and tool holder and the part we're machining. We cut the groove in the part, and it's worn. And every 5 parts we cut, or 10 parts, or whatever the right number is to keep that so I make the part with the right precision, I take the tool holder and the tool off the machine. I release the grip that is holding the tool, and the spring pushes the tool down to a setting block. And then I retighten the grip and put the tool back on the machine. Several things have happened that are very different. The head and the relationship with the bed of the machine and the work pieces has never changed. Only the tip of the tool has changed. And now it's done by a setting. It's done upstream of the process rather than downstream. So here's what I've eliminated. Michael Harry, and Rigel Stewart, when they were analyzing variation, concluded that the Japanese had less variation, but they assumed that they were doing it with statistical process control, and that's not correct. They were not doing it with statistical process control. They were doing it with settings. We eliminate the data collection. We control the process upstream of the variation. We eliminate most of the opportunities for setup mistakes. About 98% of the setup mistakes can be completely eliminated. And we cut the setup times by 97 to 99%. In other words, the setup times take 1% of the time it used to take when we were controlling processes with statistical process control. So here's an example. C-135, they spent $100 million refurbishing this aircraft. They're pumping it up, pressurizing the airplane. The pressure comes up. There's no needle on the gauge. It goes past that. The worker comes up and says, oh, we're not up to pressure yet. He walks away, and the plane ruptures like a balloon. $100 million loss because the plane was overpressurized. They were doing a pressure test. You have to pressure test an airplane because it goes from low altitude to high altitude. Simple solution is to have a pop-off, a burst disc, pressure relief kind of thing so that you pressurize to a setting. The setting determines when the pressure is reached. When it breaks the burst disc, it could whistle and tell you that the task is done. But you should pressurize to a setting and not by an adjustment. One of the most important things that you can do is to convert your explanation of your problems to one-page reports. You can develop one-page reports in your own company that describes the before and after conditions, that puts the information available. Instead of sharing how bad a job somebody did, that Joe made a mistake and it cost the company this much. Show people what you've done to fix the problems. Put the positive on it. I did this. Our team did this. It can change it from the negative to a very positive experience in terms of quality control. We have on one page the part, the problem, the evaluation, the priority. We have the inspection method, the control method, the description of the before and after, ideally a picture. We have a description of the method for the solution. There are mistake-proofing opportunities everywhere. They're in the product use, in the product design, they're in the production equipment, they're in the process, they're in the information. Lots and lots of opportunities everywhere you turn. We work always to convert adjustments to settings. We eliminate the need for statistical process control. And we don't believe that you can we don't just believe you can achieve outstanding quality. We know that you can. You can do this in a remarkably short period of time, and it saves yourself a lot of stress and your company a ton of money. The SMS method is the only method that dramatically improves quality and saves money. Simplifying can eliminate half the mistakes with enormous savings. Mistake proofing can eliminate or control virtually every mistake and pay for the investment. And setting can control variation, eliminate 98% of the setup errors and setup time and the adjustment mistakes in making adjustments. And so the SMS method is the way that you get to outstanding quality and do it at extremely low cost. That is what constitutes world-class quality. So what is the purpose of a strategy or a huddle if you never pass, kick, run, or score? The whole purpose is not what you know about quality, it's what you do about fixing your quality problems, and I want to emphasize that. Now, Paul asked a question about the software. The software will be available after the 4th of May. We're going to introduce this at the ASQ conference. And if Paul can provide me a list or wants to send out a link, I will send a link that you can use after the 4th of May on that. Any other questions?
First, one of the questions is, if it's so obvious that quality pays through mistake proofing, why do so few companies apply mistake proofing?
Excellent question. The reason that most companies don't apply mistake proofing is two things. The first problem, the most important quality discovery in the history of mankind was standard measurement methods and standard measurement tools that first applied in a production environment in 1906 in the Ford Motor Corporation. That was what helped us find the problem with variation. The method of statistical quality control was invented in 1923, came out of Bell Labs, and that became our paradigm of controlling quality. Well, what's happened compared to 1923? Our control of variation has improved dramatically. The equipment is better. Our understanding of the problem is better. We can hold tighter tolerances. So what's happened is over time, the control of variation has improved dramatically. We cannot let it go. We still need to control variation. But the paradigm is what drives the way we think about fixing quality through that process, and that paradigm is so deeply embedded that we don't realize or appreciate the importance of mistakes in modern production. It is kind of like a river, and when the water flow is high, we don't see the rocks. As we lower the river, we're getting lower and lower until the rocks are appearing, and now the rocks are the dominant part of the problem. And that's exactly what's happened. We haven't, as a society, fully recognized the significance of that transition, but it has already occurred, and we need to start to recognize how we need to change our quality control methods to get to those outstanding levels.
Martin, should we get operators involved in the error proofing, the creation of error proofing and mistake proofing? And if so, how do we do that?
Let's see. Yes, operators definitely need to be involved in it. There's several things that they need to be involved in. First of all, the truth is they see more of the errors than we see. We don't know what's going on. They do. Only when they get involved will we really understand the extent of mistake proofing that's required. The best companies typically have one mistake proofing device for every 12 seconds of work, or 12 mistake proofing devices for every 60 seconds, or one mistake proofing device for every 5 seconds of work. And so they see the problems. They can help us identify where they need to be implemented. But more importantly, they often have great suggestions for improving it. And they also have to live with the devices. They can tell you what works and what doesn't. And so they contribute a lot to getting proper devices deployed. Now, how do you get involved? The best thing is you don't need to train them the same way you would engineers or industrial engineers, but they need to be aware of what mistakes are like and what they need to look for. They need to understand the basics of what a mistake-proofing device should look like. Training for them is a fraction of the time it takes. We'll spend a day and a half for industrial engineers and design engineers, a day and a half to 2 days, but for the workers on the factory floor, 4 hours. And that can be broken up in modules so it can be covered in lunchtime periods over a period of time. But yeah, without getting them involved, you never get all the things fixed that you need to.
Great answer. You mentioned eliminating data collection and putting in set points. Is that always going to be the case? Are there instances where you still need to collect data? And if so, can you give us an example?
On instances where you still need to collect data, most of the data collection is done prior to the deployment on the production line. For example, if I have a tool where, like the milling machine that I was talking about, I need to know, one, how many times I can make a cut before I need to do a setting. So I need to collect data before that goes onto the production floor. And then I also need to know how many cuts I can make before that tool has to be removed from the machine. I use a counter with that to determine when that needs to come off. There is data collection. We should always be tracking the nonconformances. Pareto charts of the nonconformances are very helpful, but I caution you that you should always look at data for long periods of time if you want to really understand the patterns. If you see a mistake once, you fix it. If you want to get the pattern of your data, you want to look at data for 6 months to a year. The problem is mistakes change dramatically. When the startup of a company, an epidemic in a hospital, there's just a lot of variables, and if you look at small data sets, you miss the big picture, and you want to start with the big picture. So look at large sets of data, and yes, you still need to characterize and understand your processes, but you generally try to pre-characterize them before you deploy them out on the factory floor.
The person that asked that question gave an example on the need for data. They're in the food industry. We receive product from our supplier and pay for that based on analytics that they test check, and we double check those because there's no known way for sampling. I think that's where the question was coming from.
Excellent. There are some things that you can't sample on, and in fact, one of the things that you learn about mistake proofing is you cannot control mistakes with sampling and inspection. Let's take something like a food product. Some chemical that's built in a batch that is inappropriate. It may be nuts, and you haven't labeled your product for nuts. The difficulty that you have is the sampling inspection is not good enough to control those types of things, and that's why the idea of we could spend more time on the concepts of of source inspection, statistical sampling inspection, and the original type of inspection, which was just a judgment inspection. And we could go through and describe how you convert the traditional types of inspections to source inspections and do 100% inspection at a fraction of the cost that we do our traditional statistical sampling inspection. You have to get your source inspections so they're inexpensive but achieve outstanding results.
Two last questions. We can achieve world-class quality by using SMS. Why, in your opinion, is it not popular among manufacturing industries like Six Sigma, ISO, other, Lean, those kind of things?
That's an excellent question. Well, first of all, some of the concepts that we've developed here are fairly new. We haven't actually been advertising or broadcasting them. This is the first broadcast that we've provided and the first time that we've published this. I think one of the other challenges is there's problems with not invented here. The issues about single-minute exchange of dies, for example, has been known for years, but it's been thought of a tool as a batch size reduction tool. We've never understood it as in general terms. There's a few industries that have. We've never understood it in general terms as a quality control tool. It was invented as a quality control tool, not a batch size reduction tool. That was this kind of the opposite. We lose so much in terms of translation as we go from one industry to another. Another issue is that companies make big investments and then it's really hard to change. It's kind of like a change in a ship. There's a lot of mass and it's headed in a certain direction. One of the problems we saw working with Lockheed Martin is when we identified the data, they had just spent several $100 million deploying a Oracle software type system, and we said that to be able to track the earliness and lateness of the parts being delivered, there's some changes they need to make in how the data is represented. And they said, we recognize the problem, we know that it would save us a huge amount of money, but we can't change the software. There are kind of directions that companies head in, and it takes a while for them to recognize that there's different opportunities that are out there.
Just one last question here, Martin. Can you explain more about what your services from your company are? Do you offer training, or how does your company provide services?
Thank you. Let's see. There are several ways that we provide services. We're working with Visual Thinking Inc. in Portland, Oregon. Let's see, we don't have the time and the resources to go in and to a company and do all the training. Our preferred method is to train company leaders so that they can do the training. We have just posted online training methods so that the webinars are available so that an instructor can use that to present them information to the participants and then run the activities, or as they develop skill in it, they can turn off the audio and they can do the training themselves. So the training is available to help people learn how to do that. We have train the trainer manuals. We have the software that's going to be available here shortly. We have we provide services in consulting. If somebody's got a real quality problem that's critical to getting addressed, we can come in and help them with those kinds of issues. One of the things that we do that I think is most important is many companies, if I go into a company that's working on medical products and I show automotive examples, their eyes glaze over. They don't understand what that means for them. So one of the first things we do as we work with the company, in a half a day we go out on a factory floor, and typically we can find anywhere from 40 to 60 opportunities and some examples of mistake proofing to help them realize how those concepts apply in their company. And you have to see what that means to me before you get really invested in understanding what mistake proofing is or the value of that. And so we help companies do those things. And so there's kind of a spectrum of services and products that we offer.
Great. I want to thank you, Martin. This is the end of our session. I guess from my own perspective, I thought I understood error proofing, but after listening to you, I realized that there was a lot I didn't understand. So really appreciate what you've done, what you presented here. Do you have anything you would like to say as a closing comment or anything before we leave?
I just want to thank everyone for participating, and I want to thank ASQ and Paul Harbath for his kindness, and good luck and wish you the best, and if there's anything I can do to help, let me know.
I am Paul Harbath, the 2015 chair of the ASQ Lean Enterprise Division webinar series. I want to thank Martin for his excellent presentation, and thank you for listening to Martin's presentation, What is World-Class Quality and How Can We Achieve It? If you have any questions about the content of this webinar, feel free to contact Martin directly. Next month, our presenter will be Michael Bawley from ESG Consultants, who will be presenting Go and See. Go and See for yourself has been from the very start a key lean management principle. But go see what? And then do what? With what purpose? In this webinar, Michael will show you how to effectively use Go and See to understand your business challenges by seeing what there is for real and what isn't, forge agreement about what is the main problem you need to solve right now to stimulate teamwork, support Kaizen by challenging workplace teams to improve their methods, and show respect for the experience of every person and engage them in problem-based learning. Michael Bawley, PhD, is a lean management practitioner, business writer, and author. His most recent book, co-authored with Freddie Bawley, is Lead with Respect, a novel of lean practice, published by the Lean Enterprise Institute. It is the third in the Lean trilogy, along with the Goldmine and the Lean Manager. As managing partner of ESG Consultants Paris, he helps executives and companies in manufacturing, engineering, construction, services, and healthcare adopt lean systems, tools, and behaviors. Michael is associate researcher at Telecom Paris Tech's Project Lean Enterprise and co-founder of the French Lean Institute. The ASQ Lean Enterprise Division webinar series is the place for you to hear the best of the best in the lean industry and learn more about how to apply lean in your application. The American Society of Quality Lean Enterprise Division is a global network of professionals helping individuals and organizations apply proven and leading-edge lean principles and practices to achieve dramatic results for your personal and organizational success. Come lean with us. Thank you for listening, and I will talk with you next month.